Indeed, my pleasure and a privilege for all of us to have one of ours to come back to give today's CAN seminar, and that's Professor Halil Ceylan from Iowa State University. And I'd like to mention that it's indeed very good to have a good friend to come back here, especially for me. We spent a lot of time together during his PhD years and my first assistant professor years. Another thing remarkable about Halil is that in his PhD work, that he primarily worked with Professor Barenberg, and I was involved with that as well. He did one of the first ever in his lab finite element program. He was able to get that all the solutions formulated into a neural network model. That actually was really showing the light to some groups here that you had some visitors on recently to see, oh, this is applicable to the payment MEPDG concept. So that's why I think his work on concrete payments was remarkable. And of course, he carried all of that onto another great concrete payment school, Iowa State, and he's doing much more than just concrete payments right now as a director of a new sustainable payment engineering research center. So it's indeed our pleasure to have you back, Halil, and we're looking forward to hearing your presentation.
Well, thank you so much, Errol, for your kind words and introduction. So I will just use this one, right? It works. Okay, great, wonderful. I can move around. So it's really a great honor and pleasure to be at University of Illinois. As Dr. Sumar mentioned, I had my master and PhD degrees from payment engineering here. And sorry, is it being recorded? Do I need to stay in a certain location for the audience? Okay, okay. I hope that, do I need to wear anything audio-wise?
You can use the lapel mic.
Okay, so if there's any audience, sorry, let me wear this. Is this on right now?
Yes.
Okay, wonderful. So if anybody is online, I'd like to make sure that they can hear us. So, and I started my graduate studies here in geotechnical engineering. Then I saw the light switch into payment engineering program. But, it wasn't planned. But if you want to go a good payment engineer, you really need to have a very strong background in geotechnical engineering. And that greatly helped me. And you have all these giants in payment engineering community here sitting with us. So it's a great honor to be in the same audience with you. So I'd like to share with you when I was contacted about the CAN seminar. I actually proposed 4 or 5 topics, and this was the one picked among them. So, and obviously, we have all these colleagues who started, the payment engineer, mechanistic-based payment analysis and design here. Sorry, I hope I didn't screw up anything here. Did I push anything? Did it? I was just trying to find it. Okay, it's here. Okay, sorry about it. Yeah. Okay. Okay. So the NCHRP 146 and many other projects follow that. And one of the things that I did at the Iowa State University was that when I first joined there in 2002, as you know, this MEPDG at the time started as AASHTO 2002, NCHRP 147. Then we started teasing with it 2000X, 20XX. Eventually, in 2011, the official copy Darwin ME came out, and I was telling my colleagues at Iowa Department of Transportation that this is the new, phase in payment engineering. We need to implement this in Iowa. It will improve the, the payment design practices. So this is one of the very first projects that I got, and I'd like to share our experiences with you on that. So we have a program called PROSPER, as Dr. Sumlar mentioned, Sustainable Payment Engineering and Research. We actually do quite a bit of things under this, the PROSPER, the umbrella. And so, the message here is that in order to prosper, one needs to invest in the infrastructure system. That's the message we want to convey. And, we actually do, as you can see, mechanistic-based payment analysis and design is one of our core expertise. But we do quite a bit of work in health monitoring, use of smart sensor systems, intelligent systems engineering, highway and airport payments, and non-destructive testing and evaluation. These are our core expertise areas. And I'd like to acknowledge the associate directors for PROSPER, Dr. Rangan Gopalakrishnan is former student of Professor Thompson here. And Dr. Kim is one of my former PhD students. And we have now 19 graduate students working in our program. So, and we actually have large number of colleagues over the years involved with this MEPDG implementation from Iowa Department of Transportation. Mike Heisman is actually one of my former PhD students. He's now an assistant director at NCHRP. And Chris Brack is the payment design, payment management engineer. And when I was studying here, Professor Thompson's class, he mentioned that one of the things that you face in these kinds of large, new developments, new concept, mechanistic-based payment analysis and design, you face a lot of, say, the challenges, okay, resistance from the upper management, because it requires a lot of new resources to implement a huge initiative like this. So it wouldn't have been possible without the support and involvement of all of these colleagues within the implementation of this program. So we had several research projects funded by Iowa Department of Transportation and Iowa Highway Research Board. I'd like to acknowledge all those colleagues and agencies here. So this is the outline of my presentation, and I'll just follow this, the topics here to cover my presentation. And you've seen these kinds of slides in your payment engineering related courses. Before MEPDG came out on this empirical based AASHTO payment design methodologies, we used to have 8-9 input parameters, and in those design methodologies, climate was largely ignored. And now if you look into the Pave ME, the latest version came out last August, 2.2, and earlier versions, one of the things that we did, the biggest changes in my opinion, was the incorporation of the climatic, the loadings, the climate into the, the payments, the analysis and design practices. Obviously, as the title, suggested, and we actually have a mechanistic analysis going on, and as you know, this is the empirical portion of it. How do we relate these critical payment responses, stresses, strains, and deformations into the predicted payment performance? And we use transfer functions, and that's why it's called Mechanistic-Empirical. And it's obviously very challenging to have 100%, mechanistic, the payment design. I think there will always be some component empirical about it, and that's the link that we're talking about, okay? So as you know, this integrated climatic model, several colleagues here in this, the audience, Barry Dempsey and others, had a huge impact in development of ICM, and they made improvements as the MEPDG, was going to be implemented nationwide, coming up with an enhanced version of it. That's what it stands for, Enhanced Integrated Climatic Models. So, and these are the payment responses that we're talking about in different, the payment layers. And this is just the, the general layouts. We have obviously, like any civil infrastructure system, we need to know what our loads are, traffic, and other loads are climate, which also have an impact on the material characteristics. We need to know the payment system configuration, thickness, joint spacing, things like that. And we put it into a payment analysis model like ISLAP, ILLISLAP, ILLIPAVE, IPAVE, GTPAVE. All these colleagues, had a huge impact developing these models. Then we use transfer functions to relate them to the payment performance. Before MEPDG came out, it was basically a thickness design, right? You're using these, the charts, and to find out what the related payment thickness is going to be for a given traffic level, easels, equivalent single axle loads. But now we have the ability to know individual, the performance, routing-wise, roughness-wise, the cracking-wise, so we can actually identify where our payment and in which mode it's actually failing, okay? So that was a huge shift going from mechanistic to, the empirical in this regard. Many of you remember that the first research-grade version of the software came out in July 2004. And it was called 0.6, the version of MEPDG. And then again, in so many intermediate versions came out all the way to MEPDG 1.1. Then in April 2011, Darwin ME came out. As many of you remember, the earlier version of the software called Darwin And obviously, colleagues here with 50, 60 years in payment engineering know where the acronyms come. The earlier version was called, the Darder, Mike Darder's son was involved with it, and Windows-based. That's where the acronym Darwin comes from. And ME was the Mechanistic-Empirical, the version. That's when it became official design guides, okay? And then in February 2013, AASHTO renamed all of their products, and then it became Payment ME, and that was the first version, 1.3 came out. And as of 2015, Payment ME design version 2.2 came out. And obviously, quite a bit of improvements that took place over the years. The biggest addition, in my opinion, in the latest release of the software, if you were able to attend the webinar, this was just a couple of weeks ago, invited webinar, say the presentation, was the addition of the reflection cracking module in it. And that was based on the work that Bob Litton and others did on NCHRP project 141. And so now it's incorporated into the Pave ME. So every time now you run, say the Pave ME for composite payment systems, it will actually use, this reflection cracking module as well. I had some involvement, as Dr. Tsumlar mentioned, developing neural network-based, the stress intensity factor predictions. There are 31 models that we developed into, which got incorporated into this. So, and that's just a quick, the overview of the developments in terms of this acronym MEPDG implementation. So, and as you can see, a large number of states are in the process of actually implementing this, the new payment analysis and design software. And, Iowa is one of the states. And then you have this question, okay, if you look into the title, it talks about implementation and local calibration. So there's this nationally, the calibrated software available. Why would you bother to, the locally calibrate this thing? And I mentioned to a couple of colleagues this morning as I was meeting with them, Iowa is one of the states with a very unusual 20 feet joint spacing, jointed plane concrete payments. Most of the payment sections incorporated into LTPP program, long-term payment performance, the typical joint spacing is considered to be about like 15 feet, and there are states, going down all the way to 12 feet joint spacing. If you use 20 feet joint spacing, you can do this thing, with the educational copy of the software as well, and it's going to predict you that in 8-9 years, 100% of your slabs will suffer from, the transverse cracking. Well, I just drove 6 hours yesterday, and 3 of those being in Iowa in I-80, Interstate 80. We know that that's not the case, and those payments have been performing really well. And that's one of the must, requirements in a place like Iowa. You have to do local calibration. Otherwise, if you want to keep your cracking and IRI values under control, you have to come up with very unrealistic, very thick, the concrete payment designs to keep those, the cracking and roughness values under control. Another state with 20 feet joint spacing is Louisiana. Mike Heisman calls me just about every other month or so. He's helping them with their implementation and local calibration process. And, that's another state that they have to do this local calibration. Otherwise, you will get very unrealistic, the values. And again, states with having not enough representation in the long-term payment performance, and if their materials, soil types, or payments, the construction practices are not being represented in the LTPP program in a proper way, they have to do this local calibration so that they can match the predicted values with their, the observed payment responses. And I'll explain these, in upcoming slides. As I mentioned earlier, in the old AASHTO payment design procedures, whether it was for flexible or rigid payments, we had 8-9 input parameters. Well, if you want to do a decent job, actually, if you count all the input parameters, if you want to do a level 1 design, you will need several hundred input parameters. For example, you need to know the gradation of the, the soils and aggregates that you're using. Well, that means several data points itself, right? You have to know the percent passing in several different sieve sizes, and you have to do, the very detailed laboratory testing and characterization to determine the, the moduli and deformation characteristics of your, the pavement materials, whether it's hot mix asphalt or Portland cement concrete or unbound and bound layers, it doesn't matter. So it's a significant shift again how we used to do pavement analysis and design. So it can actually be overwhelming. You know, if you get used to all design procedures, suddenly you will need to worry about how you're going to get all these input parameters, you know, for a given pavement system. So then, you know, during this initial implementation stage, you know, the management, upper management from Iowa DOT was asking us what new equipment that they need to get and what new characterization that they need to do for their pavement materials. And obviously, they needed to, you know, resources are quite limited, and they need to focus on certain, you know, the pavement input parameters. And that's why we did a lot of, say, the sensitivity studies within Iowa. Then, you know, there was a national project, NCHRP 147, you know, focusing on the sensitivity analysis of these, you know, the MEPDG models that have been developed. So I had the honor of working on this project with our colleague Chuck Schwartz from University of Maryland. And, you know, we looked into the definable, you know, the input parameters like slab geometry, thickness, and all that, and then look into the, you know, the base and subgrade values, and the, you know, and then all on this refinable, say the payments, say the input values like traffic, vehicle speed, and all that. So we came up with an approach, you know, to study, do a large number of runs and find out what will be the most significant, you know, most, say the impactful input parameters that affect, you know, the pavement performance. So we look, you know, we look at the pavement surface layers, pavement foundation layers, and all of that. You know, before then, many of these studies, sensitivity studies, what Chuck and I call it is the yo-yo graph. You know, in the x-axis, for example, you vary your, say, the modular of your surface layer, and in the vertical axis, you then try to characterize how your cracking or pavement roughness is being changing. So there has not been a systematic and a comprehensive effort gone into the sensitivity. So sensitivity analysis is actually a science. There are colleagues dedicating their entire lives, you know, working on these. And one of them is Satelli from Italy, actually. And you can see a lot of studies on this. And we came up with a global sensitivity analysis approach. And, you know, we came up with new definitions in pavement engineering to determine, you know, what's the low sensitivity input parameters on, what are the high sensitivity input parameters are. And if you want to look into the sensitivity, as you can see, if you look into this like Caesar type formation, you can actually have a very small, you know, movement opening here, and it can have a large impact. Or even if you have, you know, very large movements here, depending on this configuration, it may not have very high impact, you know, on this opening. So this will have a very high sensitivity definition-wise, and this will have a low sensitivity. So we did a very large comprehensive study varying all of these input parameters, but all at the same time, not like a yo-yo graph, one at a time, but we changed them in a global, you know, the environment. That obviously required a very large effort. At some point, we were running 120 computers in parallel for several months to generate about 100,000 MEPDG, you know, the runs. And as you can imagine, just making that many large number of runs, you have to write computer codes, and you have to automatically, you know, the post-process the data, and it was a very huge effort. So, and you know, we came up with these kinds of local sensitivity analysis and global sensitivity analysis type approaches. And you know, the report and several conference and journal papers coming out of this are available on the internet, so you can easily access them. And so we came up with some very initial screening to eliminate the input parameters that we all know was not having any impact on the, whether if you used maximum values on the pavement performance. Then based on this one at a time local sensitivity analysis, we came up with a large number of input parameters that went into this global sensitivity approach. And then we came up with response surface models. And obviously, as human beings, you know, with our eyes, we can only detect 3 dimensions, right? So as you can see, you know, here is an X, Y, one at a time, you know, the local sensitivity type of an approach. You know, change X in certain amount, and you can see how much it's having an impact on the Y-axis. But if you come up with these response surface models, then you can actually incorporate n dimensions. So you can then focus on the sensitivity values by looking at the gradient at any point in this three-dimensional world, or then you can generalize it. You can look into any n-dimensional world, okay? And again, you know, having background on artificial intelligence and neural networks was actually of huge help. We were able to actually map the MEPDG solutions so that we can actually come up with very, you know, the speedy, say the calculations of these slopes at different locations, which gave us a much better understanding of the input parameters, you know, having a global impact on the payment performance, okay? So again, as you can see, we utilize these kinds of artificial intelligence, computational intelligence tools, okay, in this project. And here are some findings, you know. I was having discussions with Professor Reisler earlier. As you can see, out of this just roughly 100,000 runs that we did, we can actually, you know, teach these models. We can map them using neural networks, like, you know, the faulting values. This is what the software was predicting, actually calculating, and these are the neural network-based predictions. So you can actually see that you can achieve R-square of 0.93. You know, what this means is that I can actually just punch in numbers into this neural network-based models without actually even using MEPDG or PaveME. With, you know, R-square of 0.93, I can actually tell you what your faulting value is going to be for a given life of the payment. Actually, that's not bad. You know, that's good achievement. And if you look into IRI, the R-square value was 0.82. And again, if you consider, you know, that this was a study covering all kinds of climate types, traffic levels, and payment configurations within the entire country, that's not bad at all. But if you try to do the same thing with transverse cracking for JPCP, I forgot to include that, you get a very low R-square. I'm always puzzled. I think that's something that needs a lot of work. We need to make improvements. So anyways, I mean, in short, out of these studies, we were able to come up with this kind of grouping, okay? So we came up with this kind of scale definitions. We named certain input parameters as like hypersensitive. If you make very small changes, it has a huge impact on payment performance. And if you need an example, coefficient of thermal expansion for rigid payment performance. A small change in CTE has a huge impact on, you know, the payment performance. So believe it or not, payment material characterization site at Iowa DOT was like a black hole. They've never done within the DOT facility itself, none whatsoever, resilient modulus testing, okay? Only studies done was part of the LTPP program where subcontractors came and get some samples. So they right away acquired the resilient modulus test equipment. And they were not measuring coefficient of thermal expansion. They started measuring that. You know, they didn't have a Nottingham asphalt tester, so they acquired it right away. All of these things happened because they wanted to implement, you know, the MEPDG in Iowa. So as you can see, when we talk about mechanistic-based analysis and design, an agency has to go through quite a bit of transformation, and they have to do quite a bit of an investment, and, you know, to to upgrade their systems and you know, so many other sections, traffic, material characterization, and other portions of the highway agencies. So within this definition, now you can see that, for example, for jointed plain concrete payments, slab width comes out to be one of the most sensitive input parameters, okay? That's why we have widened slab concept, right? So to keep the payment stresses under control. The modulus of rupture, for example, the thickness, you know, and you may even wonder, my God, why is and how unit weight comes out to be as an important input parameter? Can you guys guess why unit weight comes out to be as a sensitive input parameter? Well, if you look into physics, if you want to know the moduli and strength of a material, you know, the unit weight actually goes into that, right? Rho, you know, the gamma is one of the multiplier. So they were actually using certain, you know, the equations from physics to calculate or, you know, predict the moduli of the, say, the strength of the PCC layer. And that's why, you know, the unit weight is one of the factors here. Plus, if you do a curling warping analysis, you know, take into account the environmental parameters, gamma unit weight is another factor, you know, that goes into the equations. So sometimes you find out some of the input parameters comes out to be very sensitive that you were not thinking that you will have, it will have such high impact. But basically, as you can see from there, including joint spacing, but material input parameters have a huge impact, on predicted payment performance. There are certain things that we were not measuring at all, like how many states still measure what's the surface shortwave absorptivity of, the PCC material. Very few, right? We're all using guesstimated, the values. I mean, you can hardly find it in textbooks. What's the surface shortwave absorptivity of PCC material? So this forces you to collect more data and do a much, the better characterization of your payment materials that you're using in your design. It forces the DOTs, highway agencies to collect, the more data. And these came out to be in the sensitive scale, and there were a number of input parameters that were non-sensitive that have obviously not included in this chart. And in terms of the flexible payment portion, I think I was mentioning this to Professor Thompson earlier, dynamic modulus comes out to be the most critical input parameter. What dynamic modulus consists of? Obviously, alpha and delta in those equations that you use, and those are very obviously the fundamentals within the dynamic modulus E star prediction. And then the thickness of the HMA layer, those came out to be hypersensitive, and you can see the good number of input parameters here, which are in the sensitive, very sensitive range, and the remaining ones are in the sensitive, okay? And as you can see here, you cannot see any, the input parameter which have all white, which means non-sensitive, and that means that we did a good job in the initial screening process. All the inputs that we thought will be sensitive actually came out to be that way, okay? And for example, the resilient modulus, and that's one of the, again, very sensitive input parameters, and that's why now in Iowa DOT, they actually require now the contractors to come up with resilient modulus characterization for new payment systems, okay? So basically, this was a very rigorous study, and very few surprises in results. That was a good thing, and but there were a couple of them, as I just mentioned. Some of them, some input parameters came out as surprises in results, and this provides a practical guidance for payment designers. And would this actually help the highway agencies how they can actually allocate their resources? Okay. They need to put their money in this area, measuring these, determining these input parameters, which affects 90% of the payment performance. And other input parameters have very small impact in overall performance, okay? So early MEPDG implementation, efforts, and how we sold this to the, the state highway agency. We told them that they will actually have more appropriate designs, and it will actually, if they follow mechanistic-based, the concepts, it will prevent premature failures, okay? You will have a more appropriate thickness design, and it will prevent you doing over designs. And this will be an excellent, the forensic tool if you have a failed payment section or early, cracking and all that, what might have caused, those problems. And then in a very, very conservative manner, and they forced us to come up with certain, what kind of savings that they were going to have. They wanted to have numbers. And our numbers show that even in the most conservative, the assumptions, they will actually have 1% savings per year in their maintenance and rehabilitation costs. And again, that was a very conservative, number, a prediction. And that was the selling point, for the, the state highway agency to move into the implementation of this, the mechanistic-based, the concept. We did emphasize that their benefits are going to be long-term, and they will start seeing the benefits in the latter portions of the, the payment life. So, and again, we started in 2002. I defended my thesis here. A week later, I started teaching at Iowa State. I was working on my syllabus here before I left, so for the courses that I was going to teach in the fall semester. And one of the things that we did was that, all these agencies were looking at each other. If you remember the TRB meetings, it was in, largest rooms full of people, standing room only. They were all trying to find out, oh my God, what does this AASHTO 2002 means? How are we going to implement this? How is this going to work out? They all had big, big question marks. And, I looked at around and I knew that Minnesota, like Illinois, was ahead of Iowa in terms of mechanistic-based concepts. Then I was thinking, if I can get colleagues talk to each other and they can talk to, Minnesota DOT colleagues, Iowa DOT ones, and they will feel a lot more comfortable that this is actually something manageable and there are really benefits of moving into mechanistic-based concept. So we came up with a tri-state meetings. And, you run into problems like you can't even have a meeting set up bringing 3 state highway agencies in any one of those state DOT locations, because all 3 of these states had travel restriction. And by law, they could only travel 50 miles from the state border. So we started having meetings in Wisconsin, a town called La Crosse, and the owner of Holiday Inn, had no idea why we were, having their like meetings every other month or so, because that was the location satisfying 50-mile radius, the requirements. So you run into all kinds of problems, but this was actually a very good thing, and we were inviting colleagues like myself, into the meetings, and researchers and highway agency representatives. We were working together, including industry representatives from concrete and asphalt, that this is the right thing, and we need to move forward. So that was very important to pass that, the psychological threshold. You have to have the management support, otherwise you can't do anything, So, and then one of the good things that we did in Iowa is that we came up with an implementation plan. I get reports, every year or so, how many of our research projects get downloaded, 1,000 times or several hundred times. So this is one of the reports, implementation plan that gets quite a bit of a downloads. So it seems like people are interested in this topic. So within that implementation plan, we identified, number of research projects that Iowa Highway Research Board and DOT needed to sponsor. So that got completed in 2005. And again, the way we were selling the idea was that better performance prediction and more cost-effective designs. And that was the 2 points that we were emphasizing. Before NCHRP 147, we did our own local sensitivity analysis, which gave actually similar findings, identifying critical inputs. We identified where sufficient data existed within the DOT. One of the areas that Iowa DOT was doing well was traffic characterization. They had a good number of weigh-in-motion stations. They actually had decent data. But in material characterization, it was a black, the hole. So they needed a lot of help there. And that's what we identified in those areas. Then we came up with a 3-phase implementation, the plan. And first 2 of them, started right away. And phase 3 was what I'm going to present in upcoming slides, whether local calibration was necessary or not, because it was a moving target as we were working on this. It started with 0.6, then they came up with 0.7, 0.8, 0.9, 1, 1.1. Every time they came up with a new version of the software, you have to redo all of your runs and understand how the software predictions, whether they were agreeing with the field observed values or not, which is the heart of the local calibration, okay? Anyways, so we started in this, the implementation plan. These are the 8 topics that we identified, and the ones in green are the ones that I was leading, and we were basically 3 pavement materials colleagues within the geotechnical and materials engineering. That's what pavement engineering program falls under at Iowa State. And so one of our colleagues was leading the first 3 tasks, another colleague was leading 4, 6, and I was leading tasks 5, 7, and 8. But I had some other appointments with Iowa DOT. I was constantly giving them updates on what's going on within the country and internationally in terms of mechanistic-based pavement analysis and design concepts. I'm just going to quickly go through these. I'm not going to get into the details, but these are some of the subtopics. For example, what we did actually in terms of Iowa traffic data, assessment of the climate data. Right now, there's like about 15 years of data in the latest release of the software available. But in the research grade, it was certainly 4 to 5 years of data was available, hourly climatic data, and that needed to actually getting, the collection of the new hourly climatic data and populating those climate locations. But luckily in these agricultural states, colleagues from agronomy department had a really good, the record of all this, what the humidity was, precipitation and temperature and all that. So we collaborated with them, came up with a 50-year historical climate database from agronomy. And my colleague, former PhD student Mike Heisman, he still does actually research projects for a number of highway agencies, helping them to populate their climate databases. So he's still seeing benefit of some of the research we were involved together earlier. So, and again, testing of the asphalt mixtures, and obviously like the dynamic modules characterization, that was a must. And again, DOT needed to invest in that area, okay? And testing Iowa PCC, the Portland cement concrete materials, you needed to have all of these input parameters, and as you saw in the sensitivity analysis, material, say the stiffness and strength values plays a significant role as expected, and we need to have actually those things characterized really well. And again, this was an area totally black hole, and what we did was I was able to convince them that if they could buy a Nottingham asphalt tester with the additional, the equipment that comes with it, we can actually use it for resilient modulus testing as well. And I think Iowa is now one of the rare states within the United States be able to utilize NAT for soil characterization as well. But we were able to make it, and that was, although it was challenging, to make the new cells and everything work under well in this system. And again, thermal input parameters for PCC HMA. And this is again another project that I was leading. Identify a number of flexible and rigid payment systems, see what kind of input existed in those projects and what we really needed for implementation, and see where the gaps, were. And so this was a critical study, and again, this was the one that we compared, for the selected composite, rigid and flexible sites, what the software was predicting and what the actually the field conditions were. And again, based on this study, we came up with the conclusion that local calibration was a must in Iowa. Otherwise, there will be very unrealistic, predictions. So, and there were other challenges. Say like, the condition of your payment systems today, you can go and measure it, do a distress identification and all that. But in order to match, do the local calibration, you need the historical performance of these payment sections, which means you really needed a good database, okay? So Iowa had a payment management information system, but there were gaps in it and some inconsistencies, and we had to actually deal with those things as well. I'm going to quickly go through these. So there's this Iowa Payment Management Program, and my colleague, Dr. Omar Smati, had significant contributions into this. And so we identified, some issues within the, payment management program that needed some improvement and enhancements, okay? And so these are the distribution of the payment systems. And as you can see, as of 2009, our project was still going on. And although Iowans are so proud of being the concrete payment state, we actually have large number of composite payment systems because all of those jointed plane concrete payments, significant portion, got overlaid with HMA over the time. And these are the number of jointed rigid payments, the sections. And we have just about 7-8% of the payments are full depth HMA within primary interstate system, and very few volt CRCP sections. So we came up with this map and identified, the key issues in terms of the implementation of the, the MEPDG. And there were some irregularities in some of these, the distresses that, existed in Iowa Payment Management Program. I'll mention those to you. Then you run into some other issues. For example, if you run MEPDG, it predicts your percent slabs cracked. But Iowa actually hires a subcontractor to do the payment distress identification work annually, and that only tells you total lane area, in terms of, the per mile or kilometer, okay? Well, you have to come up with a conversion factor now, for example, rigid payments as well, converting the total length of the crack, that you have from the scanning, that into what actually that means in terms of the percent slabs crack. So you have a mismatch. You can't continue unless you resolve this issue here. And so one of the things that we kept doing was we report all these bugs and challenges we face to the implementation efforts, like ARA, Applied Research Associates, colleagues overseeing these efforts. And eventually an equation like this, was formed. So you can actually go into the percent slabs crack based on the, the total length of the cracks that you were getting from the, distress identification efforts, okay? And, so again, all of these issues have been reported and certain suggestions have been made to the DOT and colleagues who were working on the MEPDG development and AASHTO panels and all that. So those have been addressed, over the time. So we were able to move forward with this, the efforts. And again, the sensitivity studies that I mentioned earlier had a huge impact. For example, if you want to do a level 1, level 2, or level 3 level, all these hierarchical levels, are you going to do the implementation based on level 3, or level 2, or level 1? But since this was first time being, implemented in Iowa, it was impossible to have level 1, say the implementation. Level 1 means all of your, say the material, say the input values has to come from the lab testing, lab characterization. And obviously that's not possible to do that because good number of your payments have already out there existing. And then what we could do was, the average guesstimated values, and we had to go with level 3 type, the implementation efforts, okay? And so that was one of the things, we had to, again, discuss with the DOT and chose a reasonable format. And you run into some irregularities. For example, you look into this so-called, the MAL post book, where they actually recorded the payment performance annually. For example, here is a flexible payment section. They have, say, the routing values. Suddenly, you realize that without being recorded in the MAL post book, any rehabilitation or maintenance activity, your routing goes down significantly. Well, that's certainly an error. If something happened on that payment system, somebody must have rehabilitated or overlaid it, so your routing went down from this level to all the way down here. So you had to take out these, the sections which had errors in them, So you have to be careful when you get data from a database, for a large number of payment systems, okay? So anyways, and again, based on the validation study, when we realized that there was a huge gap between the software predictions and observed payment distresses, that forced us to do a local calibration effort. And I'm watching my time to wrap it up in time here. So we obviously had to work, the network level calibration. And again, that was level 3 based on the hierarchical, the design levels. And this will cover, the representative distresses. Although Iowa doesn't have, any significant variations within the climate, but we made sure that we had payment sections from western, central, and eastern Iowa. Obviously, you have to look at your load levels, which is traffic, mechanical loadings. You make sure that you have sections with low, medium, and high traffic. And also understand that depending on your soil types and all that, you have representation again from typical, the parameters. So based on those, we selected 35 payment sections for rigid payments, 35 for flexible. And again, given that 70-some% of the primary interstate consist of the composite payment sections, we had 60 sections for composite payments. And so this slide is the heart of this presentation. So I can summarize it, everything here. As I mentioned too, Iowa is one of the states with very rare 20 feet joint spacing, and although rigid payments have been performing very well. So if you use the nationally calibrated distress models, okay, so this is what the actual payment performance is for a large number of concrete payment sections. In the horizontal axis, you have the measured payment roughness values. In the vertical axis, you have the predicted IRI values coming from the MEPDG. Well, look at this. And as you can see, MEPDG was certainly over-predicting the payment roughness values. And the reason is IRI is obviously a combination of the transverse cracking, faulting, okay, site factor. And because it was over-predicting the cracking and faulting because of 20 feet joint spacing. For example, if you were here, your measured IRI is 100 inch per mile, but actually what's being reported is, so what's being calculated is like 220 and 30. That's more than 100%, the increased difference, which is not acceptable. But once we do the local calibration, look at the shift from here to here. So if you look at the standard estimate of error, the national one gives you a value of 50, and local one brings it down to like 4.4. And that's obviously 12-fold increase in your, the prediction accuracies. And that's why you have to do the local calibration, okay? Otherwise, you're going to have very unrealistic predictions, okay? So this summarizes the entire thing. So you can actually have very significant improvements in your predicting, your forecasting, your payment distresses. And how is the picture for flexible payments sections? And as you can see, because joint spacing was not an issue here, for example, I can talk about IRI values again. That's what public cares, right? Payment roughness. We just want to have a smooth, quite right. So the measured IRI versus predicted IRI, through our local calibration efforts, we were able to make about 8 to 10% in terms of the improvement in standard estimate of error. But what we can tell is that the nationally calibrated the values was actually not bad, but you could still make improvements by focusing on the payment sections, flexible payment sections in Iowa. So we were able to bring down the error for this one as well. So again, just the initial phase, quick say the summary, local calibration of faulting, transverse cracking, and IRI values for rigid payment systems was a must, and we were able to make the significant improvements in those areas. And we identified certain factors that increases the accuracy of routing predictions, and to a lesser extent, the longitudinal cracking and the HMA payments and HMA over JPCP composite payment sections. So, and as we were wrapping up this thing, the MEPDG software, it was 1.1, the latest research grade version available. Then they came up with a new version of the software. It's a moving target. Every time they improve the models, this is bad news for state highway agencies, but it's the fact of the life. You have to redo a local calibration because otherwise, for example, they used to have 5 calibration coefficients for IRI. Now there are 4. Well, it seems like the model itself changed. So you have to do a local calibration. Otherwise, you won't be able to use the software, okay? So then we had to redo this study, and that's what we're wrapping up right now. And the student that I acknowledged on the very first slides, Orhan Kaya, he's wrapping up, he's defending his thesis in about 2 weeks. So, and for example, I can show you some slides. I actually have a database that I keep all the way from the unofficial copies of the MEPDG and starting with the official release in 2004.6. Every time a new version comes, I run it against all these, the input parameters we have. And then from there, you can actually determine what actually has changed, to predicted payment performance, and you can actually determine whether the changes are significant or not. And so, to do that nationally, we also have representative payment sections. And believe it or not, climate has a huge impact for every time a new release of the software comes out. Whether you have cold, dry, cold, wet, hot, dry, hot, wet, or temperate climate you have. And these are the climatic locations that we use for that representation. Obviously, again, you have to keep in mind that you have to also have different traffic levels, low, medium, and high. For example, during one of the changes from MEPDG to Darwin ME and Payment ME, you can see the versions here. For example, let me show you what's happening with IRI just for the ease. And for example, in MEPDG 1.1, you were getting an IRI prediction of 141. And then when Pave ME came out, that becomes 184. Well, that's a significant change. 40 inch per mile for a payment section, that's significant enough. And so or if you had 150, that becomes 190, 180 become 230. But that was for, look at all these climatic locations, cold, dry, low, medium, and high, cold, wet, low, medium, and high. Well, if you were in Phoenix, hot, dry climate, that was not a problem for you. So now you can have two state highway agencies talking to each other, and one may say, I haven't seen any significant changes. Another guy may say, no, 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 IRI values changed greatly, and both of them will be right. And because their climatic locations are different. So if you do a systematic comparison like this, you can actually understand what changes from one version of the software to the next, okay? And here are some more, again, the comparisons. I'll just quickly skip them because of time limitation here. But I believe this presentation is going to be made available to you, okay? So, this is a good way of keeping track of what actually changes over the time to different, the payment performance, cracking-wise, rotting-wise, IRI-wise, and all of that, okay? So again, in the latest version of this, say the phase of the study, this was the initial local calibration study that we did. You can actually download it from our Institute for Transportation, say the website. In the latest one, Pavement 2.1, again, we had to redo this, say the local calibration, and also examining the software, what actually has changed from earlier versions to the latest version of the software. And again, as you can see, we had that 130 payment sections included in our study. And these are the geographic distributions. And as you can see, different, say, the soil types, climatic locations, and payment types are included in the study. And again, these are the payment distresses that we focus on, okay? And here are some statistics on, the annual average daily truck traffic, construction years. You have to make sure that you select payments with different ages as well to get that continuous, the progress in payment distresses, thickness-wise, base thickness-wise. And these are the distribution of the faulting, transverse cracking, and IRI values within the payment management database. Same statistics for flexible payment systems, traffic-wise, age-wise, thickness, and the base thickness. And these are the payment performance values, rotting, HMA rotting. These are the notations that exist in the payment management system. We just use the same ones for the ease of the state highway agency colleagues. They can easily understand it, okay? So anyways, I mean, just to show you that we have very representative, the payment sections with different, the payment performance values. One of the questions in the local calibration is, there are studies, colleagues, and they just look at the, say like you have 8 calibration coefficients, and they randomly vary them, and every time they vary the calibration coefficients, they look at how the payment performance are being affected. So it's actually a blind approach. You're not really sure what you're doing, okay? Just by luck, you may get a really good match, but then you have large number of payment sections. You have to repeat this thing. So Orhan did an excellent job using nonlinear optimization techniques, very similar to the global sensitivity study that we used. He was optimizing the error in a global city environment, and used all kinds of different approaches. And he's going to be actually presenting at the TRB annual meeting next January, summarizing his findings on this city approach. Okay. So again, we keep track of the bias, standard estimate of error, the R-square values, and there are all kinds of different indicators like mean absolute percentage error. Not much used in payment engineering, but I think this is a great indication of your ability. So what I'm going to do it is in upcoming slides and show you, in one big slide here. For example, on top left, you have the national calibration values. And again, these are the measured faulting, and these are the predicted ones. And in the first phase of the research, we were able to bring this to MEPDG version from here to here. And I know this is not a great picture, but much better than here, okay? And now in the local calibration one, we were able to bring it down to this level. So you can actually see the statistical indicators that there are 8 coefficients, calibration coefficients, and average bias, standard estimate of error, line of equivalence R-square and R-square values. I was at TRB annual meeting last year, which is 2014 TRB. Our colleague Mike Darder was the presiding, the officer for the session, and somebody was showing a curve a distribution of the data and R-square values were so high, they just fit an equation to the line, and I could not believe it that they needed to present the data in this line of equivalency. So, and people do not believe that R-square can be negative. They think that it's a number you calculate and you take the square of it. That's not the case at all. As you can see in the national one, in this case, R-square is actually negative. Do you guys know what negative R-square mean? It means that you have the wrong form of the equation. And that's why we are not able to improve the predictions anything beyond this thing. I can actually use, the computational intelligence tools. I can make this a perfect prediction, but I don't have that ability because I'm not able to change the function. Imagine that you have a sinusoidal distribution and you're trying to fit a line. Well, you can optimize it to death, but you're not going to get good prediction because you don't have the right form of the equation. So I came down to Champaign, had really in-depth discussions with colleagues here at ARA, wonderful minds. They all agree with me, but then they say that if they open the door, let every state highway agency come up with their own set of functions, they are so afraid that it may get out of control, okay? They say that you know what you're doing, but Joe Schmuck may not know what he or she is doing, okay? So that's why, you may think, that's not a great picture, but that's as good as it gets because I can only play with the coefficients, not with the form of the equation. I'm not able to change it because I'm not given that ability the way the software is made available. I think this is something that we need to think about, and perhaps, in the future we can make some improvements. So that's I think a point that we need to keep in mind. And here's what happened with the validation set. Every time we had a calibration and a validation set, obviously very similar picture, but still, if you look into where we were at nationally, for example, the standard estimate of error, and we were able to bring it down significantly, with the newest local calibration efforts, okay? So here is the transverse cracking. And I was telling our colleague Jeff Racer earlier that, with 20 feet joint spacing, look at this. In every time in Iowa you run the software, your predictions are going to get out of the roof. It's almost going to go above 100 and, compared to measured predictions. And I write on those payments every day. I know that they are not cracking at all. So in the first phase, we were able to bring down the, standard error, from 31 to 10. And in the latest phase, we were able to make it a little bit more reasonable, but still that needs, in my opinion, improvement. But, it's something that you can leave it perhaps. That's what I was trying to tell earlier. If you use the national software, I zoomed in on this slide, particularly. This is the transverse cracking. Look what happens in the nationally calibrated software. It tells you that in 5-6 years, you're going to get like 40% cracking. And that's what actually the payment performance data over the years, this payment was about 12 years old. And through the local calibration, we were able to keep this under control and bring it down to a much reasonable prediction compared to this red line. And that's what local calibration is all about, okay? Bringing your software predictions much, more agreeing manner to the field observations. And again, here are the IRI values. I showed this to you earlier. As you can see, the R-square values was 0.47 originally, and we were able to bring it down to 0.71. That's a significant improvement. I think it was well worth doing this, the effort. And in terms of using this MAPE, anytime you have values, below like 0.1, that means that you actually have a really good, the match. And as you can see, in the newest local calibration phase, these values are below 0.1. So we had actually significant improvements in predictions of the payments, the distresses through this local calibration effort. Here is, for example, the picture for flexible payment systems. There are still improvements, but obviously not as significant as compared to the rigid payment sections. And the longitudinal cracking, and I know that some of these models in MEPDG still do not work well, and certain NCHRP studies are underway to improve these models, okay? Alligator cracking, thermal cracking, okay? And rotting, we were able to improve the, the R squared just a little bit, not significant, but, still some improvements. So, and key findings, this is just a quick summary of what I was talking earlier. In certain cases, there weren't really significant differences between nationally calibrated one and our local calibration efforts, but in especially rigid and composite payment systems, as you can see, there are significant changes in the statistical, the performance indications before and after local calibration. So I'm going to quickly go through these. We talked about these earlier, and you can see the new set of calibration coefficients that Iowa DOT needs to use after the local calibration effort, and that's what they are doing right now. And they are running the software and doing some checking and comparing the performance. For example, I was just presenting these to Jeff's one of grad students. He's about to graduate. Dan King, he started a job at Iowa Concrete Paving Association now. That these are the nationally calibrated coefficients, and these are the ones that we came up with after the local calibration. And as you can see, except 2 parameters here, all others actually have changed, and that was quite a bit of an effort for faulting, cracking, and IRI. If you go into these efforts, you understand that by physical meaning, you're not going to need to play with these C6 and C8. And these are the values for new flexible payment systems, okay? And as you can see, the values that have changed are shown in, say, the red color here, and that's for composite payment systems. So for every payment type, there were good number of calibration coefficients, sometimes significantly changing from 7 to 2.3, for example, in this fashion. So, and again, importance of implementing, say, the mechanistic-based, the payment analysis and design tools. Many people think that it's only a thickness design tool. That's not the case, okay? And we want to emphasize that. And obviously, if you implement these kinds of comprehensive mechanistic-based design tools, you're going to prevent premature failures and come up with much, the cost-effective maintenance and rehabilitation, say, the efforts. And so this has been a great experience and a huge improvement in Iowa's payment analysis and design efforts. And we made quite a bit of enhancements, over the years, by closely working with colleagues from, say, the Iowa DOT and Highway Research Board. We were the only educational institution involved during the beta testing of the latest release of the software, Pavement ME 2.2. And all these years, we researchers have been complaining that, hey, why don't you let, the stresses and strains and deformations, available to us? Guess what? They are making it available in the latest release of the software now, if you don't know about it. And they are called APIs. If you're in software business, you know what application, the programming interfaces mean. And so they are starting with Julia, Jacob Uzan linear elastic analysis, if you're wondering where the initials are coming from. And as you can see, you can actually get payment, say the responses available every time you make a run. And I think that's a great improvement. And so we had the honor of checking these APIs in several different computers and platforms, 32-bit, 64-bit, and all of these things, and reported hundreds of bugs because it was a beta version. And now they made significant enhancements. And again, I had the honor of being part of the efforts on implementing the reflection cracking model. In my opinion, again, it's the most significant enhancement since the first version of the software came out in 2004, and these are the other enhancements that they were able to come up with. Every version they are adding more data into the climate data sets, and that's the one that I was talking, Marshall, earlier in the MAP-ME. This is, they are trying to link into the payment management, geographic information systems. If you have the map of Illinois, for example, you will be able to click on, for example, I-57. It will bring out the data to you related to Pave ME and all that, and they are dealing with some other improvements, high quality traffic data in LTPP. Those are the other enhancements in the latest release of the software. So I apologize, I went a little bit over time, but thank you for listening to me. I appreciate it.
only a professor can do 100+ slides in about an hour. So, you know, so, I know we're overboard, but we'll still entertain it. Questions if you have, quick questions?
Halil, question
Yeah.
last point. So one of them is, you said you had 100,000, around 100,000 simulations from MEPDG. Did you consider any material design, experimental material design for coming up with those 100,000 or so many simulations? And given that, like that huge database feeding to neural network will cause, and there is a high chance of getting overtraining. How did you handle that?
Okay, well, excellent questions. Yes, we were careful. First, keep in mind that 100,000 deals with composite, rigid, and flexible payment systems. And based on the feedback that we were getting from the NCHRP panel, and they were like, for example, regular, for example, flexible payment system, and they wanted to redo all of the runs for a stiff base, okay? So there were large number of payment sections involved in it. And also, you can, for example, characterize traffic as numbers, low, medium, and high, but what do you do with climate? How are you going to handle climate? You're not going to go into the climatic database and change the numbers, right? Wind speed and humidity and precipitation. You could only do them different climatic regions, like that's why cold, dry, hot, wet. So we had to come up with 5 different climates and 3 different, traffic levels, plus different payment types. So if you consider the number of runs being made for each individual payment type, it's not more than, a couple thousand, okay? So we were using the Latin hypercube, the technique in populating, make sure that we have, the just enough representation. I think report is several hundred pages long, just one of the topics that I mentioned here. So this was really the minimum number of runs we needed to go with. And yeah, we do have experience with using, the AI tools, computational intelligence tools, and you can actually control the software itself, and we've never run into any overtraining and all that, because we have a training set, testing set, and a validation set, and if all 3 of them giving you the similar, the predictions, that means there is no overtraining going on. So we check the training progress and all of those things, okay? But good questions. If one is not careful, you can easily make mistake in those steps. Excellent point. So,
Marshall?
Every version of the guide that comes out, do they go back and recalibrate, or do they use the original transfer functions?
well, they make improvements, right?
Yeah, but when they come up with an improved version of the software, do they drop back and recalibrate against the original database?
Well, if the database changed, they have to redo the calibration. But say like they came up with the reflection cracking module here, right? If nothing else has changed, they didn't really have to do the recalibration, national one for the other models. If they haven't changed anything about rigid payment inputs and the rigid payment database, then they don't have to redo the calibration. But we watch every version of the software. There are always, even if it's minor, there are changes taking place. That means something have changed. Obviously, they publish the nationally calibrated ones. You can actually see the calibration coefficients and how many they are. Sometimes they even change the number of calibration coefficients they have. Like for, say, the IRI, it used to be 5, now it's 4. And so they are actually changing things, okay? And you have to keep an eye on them, so.
One quick comment is the local calibration versus national calibration. Some of your values, how different from the national values. When you see national is 1 and your value is 0.001, like granular material, granular base rutting. Doesn't this more tell you that model is producing garbage probably?
You're right. You're right. Yep, absolutely. Absolutely.
How can you correct that?
Yeah. For example, the low temperature cracking. You don't need to recalibrate it because the model itself is not working well, and that's why there are ongoing NCHRP studies right now to address that problem, and they recognized it, okay? So there's this ASHTO subcommittee on payment design, Judy Corlilay, I believe, is the leading person, and Chris Brackey, Iowa DOT's payment management and design engineer, he's part of that. So the committee oversees, they check what kind of research are being done and or completed, and then they come up with a ranking procedure. And like reflection cracking was like that. When they saw that that study was conducted, finished and successful, they said, okay, we need to have this incorporated. Then the fees that you're paying, $5,000 per license, and so that money is being used to fund new research and make upgrades and enhancements in the software system. That's how it works in a quick summary. So.
I like the term S sub E over S sub Y.
Yep.
If that's near 1, it means it's a horizontal line, right?
So, Ernie?
I saw something the other day on a program that was just put out at Smart Bridges, where they have put out, somebody has put together the whole thing for instrumenting and determining smart bridges to see when anything goes wrong and that sort of thing. I first heard of this 20 years ago, and it's taken a long time. My thought is, has anybody given any thought about smart pavements, of what we need to do? I think this is the process of what we would need to do might give us a lot of insight into what needs to be done for future research.
Yeah, so I think you have a great point. There are all these advances in sensor technologies, sensing technologies. Right. So we have projects underway as well. And now these, new sensor systems, they're actually very affordable. You can buy, like $30, $40 sensors, which gives you the ability actually to use large number of them to capture the overall payment response and behavior. And obviously, the more instrumentation we do, and we do continuous and long-term monitoring, all of that collected knowledge and data are going to help us, to calibrate our models, to come up with better predictions in the future. MEPDG is just a skeleton. We're going to be able to improve certain, the portions of that model, as we have more resources and time. And obviously, I think that's going to help us. For example, if they have an improved fatigue model, and we may be able to incorporate that, and which may give us better, the transverse cracking or IRI predictions over the long term. So, and all of these things are actually interconnected, to each other. So, I'm not sure I answered your question, but
but we have a lot of these with the models. For example, even the coefficient of thermal expansion varies from site to site. Yep. Nobody has yet given me a good explanation of why in the Piedmont region they can build 30 and 40 foot long pavements and they don't crack. Yep. And I'd get 2 cracks in every slab if I tried that.
Yeah.
And if we put in our standard numbers for climate and coefficients, it would not explain that. And so there's something there that we're not putting our finger on, is what I'm getting at.
Yep.
And we need to find and think that through again. With the more information we get, the more we think that through.
I think to understand the cause of that, why it's happening in one place and not happening in another place, we have to have a really good handle on climate and also, the understanding how payment is responding to that environment, which means a lot of instrumentation and monitoring. So, and those can help us to understand the causes of such behaviors. So.
All right, that sounds great. I think that concludes the presentation. This has been wonderful. Thank you very much.